Somewhere in the dark between stars, a dead sun is spinning. Spinning so fast, so steadily, that it keeps better time than any clock human hands have ever built. Welcome to the Sleepy Lab. Tonight, you will drift through the life and death of massive stars, through the strange compressed hearts they leave behind, and toward one of the quietest, most precise objects the universe has ever made. If this is the kind of journey you want to take each night, there is a subscribe button waiting for you, one sleepy soul at a time. Now, let's begin. A pulsar is a neutron star, and a neutron star is what remains when a very large star dies. Not a gentle fading, not a slow dimming like a candle running low. A star that ends as a neutron star goes out violently in a supernova, one of the most energetic events the universe permits. To become a neutron star, a star must be born heavy, roughly 8 times the mass of our own sun at minimum, often much more. These are not quiet stars. They burn through their fuel quickly, living bright, short lives measured in millions of years rather than billions. Our sun has been burning for about 4.5 billion years and has roughly the same again ahead of it. A star 8 times its mass might last only 20 million years before the end comes. And when it comes fast. For most of a star's life, 2 forces are in balance. The outward pressure of nuclear fusion, the energy released as hydrogen fuses into helium, into carbon, into heavier and heavier elements, and the inward pull of gravity, patient and relentless, always waiting. When the fuel runs out, gravity wins. The core collapses. Not slowly, not gradually. In less than a second. A core larger than the Earth, thousands of kilometers across, is compressed into a sphere roughly 20 kilometers wide. 20 kilometers. You could drive that distance in about 15 minutes on an empty road. And yet, inside that sphere, the mass of a star. The numbers that describe a neutron star are the kind that resist easy understanding. They are simply too far outside anything we encounter in a human life. Consider this. If you could take a single teaspoon of neutron star material and somehow bring it to Earth, that teaspoon would weigh roughly 4 billion tons. Not 4 billion grams, not 4 billion kilograms. 4 billion tons. The entire human population of Earth, every person alive right now, weighs somewhere around 500 million tons combined. A teaspoon of neutron star would outweigh us all 8 times over. And yet that teaspoon would be, in some sense, ordinary matter, just matter compressed to a density the universe rarely allows. The surface gravity of a neutron star follows from this density in a way that is almost impossible to hold in the mind. On Earth, if you drop something, it accelerates toward the ground at about 9.8 meters per second squared. That is what we call 1G, the familiar tug you feel right now, pressing you gently into your bed. The surface gravity of a neutron star is approximately 200 billion times stronger than that. 200 billion grain. An object falling from just 1 meter above the surface of a neutron star would strike it moving at a significant fraction of the speed of light. Nothing soft survives there, nothing fragile. The physics we use to describe everyday materials simply stops applying. And yet, the neutron star has a surface of a kind. It has a crust, a thin layer of iron nuclei, compressed and arranged into a crystalline lattice, sitting atop the vast interior of packed neutrons below. This crust is thought to be the strongest material in the known universe. Not strong in the way we usually mean, not like steel or diamond, strong in the sense that it can withstand pressures and stresses that would reduce any other known substance to something unrecognizable before it finally fractures. Beneath that crust, the neutron star is composed almost entirely of neutrons, the neutral particles found in the nuclei of ordinary atoms, packed together at what physicists call nuclear density. Nuclear density is the density at which atomic nuclei exist, the tiny, almost impossibly small cores of atoms. A neutron star is, in a sense, one enormous atomic nucleus, about 20 kilometers across. The neutrons are not floating freely. They are pressed together so tightly that the usual rules of matter, the rules that give solids their shape, liquids their flow, gases their lightness, no longer apply in any familiar way. What lies deeper inside, toward the very core, is genuinely unknown. Some models suggest the neutrons themselves may dissolve into their constituent quarks under sufficient pressure, forming a state of matter called quark matter that has never been observed in any laboratory on Earth. Others suggest different exotic phases, different arrangements of matter that our physics can describe mathematically but cannot yet confirm. The equation of state of neutron star matter, the precise relationship between its pressure and its density, remains one of the open questions in nuclear physics. We know what a neutron star is, broadly. We do not yet fully know what it is made of, deep down. And from this object, this compressed, dense, almost incomprehensibly heavy remnant of a dead star, something remarkable emerges. A beam of radio waves. Two beams. In fact, one from each magnetic pole. A neutron star inherits its magnetic field from the star that formed it, and that field is compressed along with everything else during the collapse. The magnetic field of a typical pulsar is roughly 1 trillion times stronger than Earth's own magnetic field. Along the lines of that field, near the poles, charged particles are accelerated to enormous speeds, and accelerating charged particles emit radiation. The result is two narrow beams of radio waves, shooting outward from the poles of the neutron star like the beams of a lighthouse. The neutron star is spinning, and the magnetic poles are not perfectly aligned with the rotational axis. They are tilted, offset, the way a compass needle is not always pointing exactly where you expect. So as the star rotates, the beams sweep through space, around and around, steadily. If one of those beams happens to sweep across Earth, if our small planet sits in the path of that rotating lighthouse, we receive a pulse. A brief flash of radio waves, arriving with the same period as the star's rotation. Once per rotation. Regular. Precise. Patient. This is a pulsar. A rapidly rotating neutron star sweeping its beam across the sky, ticking out the seconds of its long, quiet life in the dark between stars. Most pulsars in the galaxy are invisible to us. Their beams never cross our path. They spin on, undetected, in the silence. But some of them point our way. And those ones, we can hear. The crust of a neutron star is unlike anything else we know of. It is thought to be the strongest material in the observable universe. Not strong in the way we usually mean. Not hard like diamond. Not tough like steel. Strong in a deeper sense. A neutron star's crust can endure pressures that would reduce any ordinary matter to nothing, holding its shape against forces that have no earthly equivalent. It will eventually fracture under enough stress. But it takes an almost unimaginable amount of stress to get there. Beneath that crust, the neutrons are packed together so tightly that the normal rules of matter no longer apply. There's no chemistry here, no molecules, no atoms in any recognizable sense, just neutrons, pressed against one another at nuclear density, filling every available space. And threading through all of it, through the crust, through the dense interior, extending far out into the space around the star, is the magnetic field. A typical pulsar's magnetic field is roughly 1 trillion times stronger than Earth's. 1 trillion times. Earth's magnetic field is already something we can barely measure without instruments. It deflects compass needles. It guides migrating birds. It shields us from the solar wind. And yet, compared to the field surrounding a pulsar, it is almost nothing. A whisper beside a roar that has no name. It is this field that makes a pulsar what it is. Near the magnetic poles, charged particles, Electrons and their counterparts are caught by the field lines and accelerated to enormous speeds, and accelerating charged particles emit radiation. The result is two narrow beams of radio waves shooting outward from the poles of the neutron star like the beams of a lighthouse. The neutron star is spinning, and the magnetic poles are not perfectly aligned with the rotational axis. They are tilted, offset. The way a compass needle is not always pointing exactly where you expect. So as the star rotates, the beams sweep through space, around and around, steadily. If one of those beams happens to sweep across Earth, if our small planet sits in the path of that rotating lighthouse, we receive a pulse, a brief flash of radio waves, arriving with the same period as the star's rotation, once per rotation, regular, precise, patient. This is a pulsar, a rapidly rotating neutron star sweeping its beam across the sky, ticking out the seconds of its long, quiet life in the dark between stars. Most pulsars in the galaxy are invisible to us. Their beams never cross our path. They spin on, undetected, in the silence. But some of them point our way. And those ones, we can hear. The first time we heard one was in 1967. A young graduate student named Jocelyn Bell Burnell was working at a radio telescope in Cambridge, England. The telescope was not the kind you might picture. No great dish turning slowly against the sky. It was an array of poles and wires spread across 4.5 acres of English countryside, built specifically to study distant radio sources. Bell Burnell's task was to analyze the paper charts the telescope produced. Hundreds of feet of chart paper, every week, covered in the faint squiggles of radio signals from across the sky. And in that paper, she found something strange. A signal that repeated, not randomly, not irregularly, but with a precision that seemed almost impossible for a natural source. It pulsed every 1.3373 seconds. Exactly, again and again. Night after night, whenever that patch of sky came into view. The signal was so regular, so artificial seeming, that the team gave it a quiet, half-serious designation. LGM-1. Little Green Men. It was not a joke. Exactly. It was the acknowledgement of something genuinely unsettling, that the most regular, precise signal they had ever received from deep space looked, at first, like it could only have been made by someone. The possibility of an artificial origin was briefly and seriously considered. Not dismissed. Considered, because the data demanded it be considered. But the universe, it turned out, had made something stranger than a signal. It had made an object. Within months, 3 more of these signals were found in different parts of the sky. Then more. They were not coming from one place. They were scattered across the galaxy. Whatever was producing them was not a single anomaly. It was a class of thing. A new kind of object, previously unknown, quietly ticking away in the dark. The name that settled was Pulsar, a portmanteau of pulsating star, though the word has a rhythm of its own that suits it. The 1974 Nobel Prize in Physics was awarded for the discovery. Anthony Hewish received it. Jocelyn Bell Burnell did not. She had been the one to notice the signal, to flag it, to insist on its significance when it might have been dismissed as interference. The decision not to include her remains one of the more quietly discussed episodes in the history of science. Bell Burnell herself has spoken about it with a grace that is, perhaps, its own kind of precision. She went on to a long and distinguished career. The pulsars went on ticking. And the more astronomers listened, the more they understood what they were hearing. A pulsar is not just a curiosity, it is a clock, one of the most accurate clocks in the universe. Each pulse arrives like the tick of a mechanism so stable, so consistent that it can be tracked across years, across decades, without losing a single beat. The timing of a pulsar can be measured to within microseconds, some of them to within nanoseconds. This precision is not accidental. It comes from the nature of the object itself. A neutron star is enormously massive, roughly the mass of the Sun, compressed into a sphere 20 kilometers across. That mass gives it something called rotational inertia. once it is spinning, it resists any change to its spin with a stubbornness proportional to its mass. There is almost nothing in the interstellar environment capable of disturbing it. No wind, no friction, no tidal force strong enough to matter. It simply continues. Turning, ticking, patient beyond any human measure of patience. The universe is very old, and most of it does not notice us at all. But a pulsar, in its quiet way, keeps a kind of time that predates us by billions of years and will continue long after we are gone. It does not know it is a clock. It does not know anything. It is simply a remnant, the compressed core of a star that died in fire, spinning in the dark, emitting its beam, ticking. And we, on our small planet, with our radio telescopes and our chart paper and our careful attention, happen to be in the path of the beam. And we listened. And we heard something regular, something precise, something that, for just a moment, seemed like it could only have been made by someone who wanted to be found. It was not, but in a way that is harder to explain and perhaps more worth sitting with quietly as you rest. The fact that it was natural makes it more remarkable, not less. The universe, without intention, without design, produced something that ticks more steadily than almost anything we have ever built. And it has been ticking, long before anyone was listening. That moment of wondering whether something regular could mean something intentional was not a passing thought that someone quickly dismissed. It was taken seriously. When Jocelyn Bell Burnell first noticed the signal in the data, it was so precise, so evenly spaced, that the team gave it a name that held both humor and genuine unease. They called it LGM-1. The letters stood, informally, for Little Green Men. It was not a joke. Exactly, it was the kind of name you give something when you do not yet have a better category for it. When the shape of the evidence points somewhere your training tells you not to go, but you cannot yet explain why it is wrong. The signal pulsed every 1.3 seconds, not approximately, not roughly, every 1.3 seconds, with a regularity that natural processes, as they were understood at the time, did not seem capable of producing. And so the question was asked, quietly and carefully, in the way that scientists ask uncomfortable questions, not with alarm, but with method. Could this be artificial? Could something, somewhere, be transmitting? The possibility was considered, not dismissed, not laughed away, but genuinely examined. For a brief period, the origin of LGM-1 was an open question in the most profound sense of that phrase. And then, within weeks, a second signal was found, coming from a different part of the sky entirely, with a different period, just as regular, just as precise, but clearly distinct. And then a third, and a fourth. Within months of that first detection in 1967, 3 more of these objects had been identified, spread across the sky, each with its own rhythm, each ticking away in its own corner of the galaxy. And that changed everything. Because whatever these objects were, there were too many of them, too varied in their positions and their periods, to be the product of any single intelligence trying to reach us. The pattern that had seemed so deliberate dissolved into something far larger and far older, a class of natural objects, a phenomenon the universe had been producing, quietly, for billions of years, entirely without us in mind. The name LGM-1 was retired. The object was redesignated, cataloged, studied. It became the first known pulsar, and the question it had briefly raised, are we alone, was answered not with a yes or a no, but with something more humbling. The universe is stranger than we imagined, and its strangeness does not require us. The discovery was recognized, in time, with the highest honor in physics. In 1974, the Nobel Prize was awarded for the detection of pulsars, though Jocelyn Bell Burnell, who had noticed the signal in the first place, who had flagged it and pursued it and refused to let it be written off as interference, she was not among those who received it. That absence has been noted and discussed and quietly mourned by many in the scientific community in the decades since. It is part of the history of this discovery, and it belongs here, in the telling of it. She has spoken about it with a grace that is worth pausing on. Not bitterness, but a kind of measured clarity. The work was real. The discovery was real. What followed was what followed. And the pulsars themselves kept ticking, indifferent to all of it. Now, let the breath slow a little more. The pulsars that were first discovered, the ones that announced themselves so dramatically in 1967, belong to what we now call the ordinary class. Young pulsars, newly formed from the collapse of a massive star, spinning fast from the violence of their birth. When a pulsar is young, it rotates quickly, roughly once per second at the slower end, up to about 30 times per second for the most energetic, 30 rotations every second, each one sweeping that beam of radio waves across a wide arc of space, each one arriving at a distant telescope like the tick of some enormous, invisible clock. But a young pulsar does not stay young. It slows. Gradually, over thousands and then millions of years, a pulsar loses energy. The same radiation it emits, the radio waves, the charged particles streaming from its poles, carries momentum away from the star. And as that energy bleeds into space, the rotation eases, the ticking grows slower. This process has a name: spin down. It is not dramatic. There is no sudden change, no visible event. The pulsar simply rotates a fraction slower each year. Each century, each millennium, the change is so small that it takes precise, sustained measurement to detect it at all. But it is there, steady and inevitable, written into the physics of the star from the moment it was born. And that gradual slowing is itself a kind of record. Because if you know how fast a pulsar is spinning now, and you know how quickly it is slowing, you can work backward. You can calculate, with reasonable confidence, how long it has been spinning, how old it is, when the star that became it collapsed and died. The rate of spin down also carries information about the pulsar's magnetic field. A stronger field bleeds energy fast, slowing the star more quickly. A weaker field allows the rotation to persist longer, more gently. So in the careful measurement of a pulsar's deceleration, there is a portrait of its interior, its age, its field strength, its history written in the language of time. Most ordinary pulsars, left to themselves, will spin down over millions of years until their beams fade and their pulses become too faint and too infrequent to detect. They do not die. Exactly. They simply go quiet. The neutron star remains cold and dense and dark, still spinning, but no longer announcing itself. And that, for most pulsars, is the end of the story. But for some, for a small and remarkable fraction, the story does not end there. Some neutron stars are not alone. They orbit a companion, another star, close enough that over vast stretches of time, matter begins to flow from one to the other. The neutron star draws in that matter, and as it falls, it carries angular momentum with it. And slowly, over hundreds of millions of years, the old, slowed neutron star begins to spin faster again. Not a little faster. Much faster. This is the process that produces what are called millisecond pulsars, and they're something different in kind, not just in degree. Where an ordinary pulsar rotates perhaps once or twice per second, a millisecond pulsar rotates hundreds of times per second, some of them more than 100 times, some more than 500. The fastest known completes over 700 rotations every single second. 700. In the time it takes to draw one slow breath, that star has turned on its axis more times than you can easily count, and yet it is not young. It is not the product of a fresh collapse, full of the energy of its birth. It is old, recycled. Some astronomers call it a star that lived and slowed, and was given back its spin by the patient gravity of a companion across hundreds of millions of years. There is something in that worth resting with. The idea that something can slow almost to stillness, and then, given the right conditions, the right companion, the right long patience of time begin again. Not as it was, but spinning, and so it spins, not winding down, as most things do, but held, somehow, in that recovered velocity, turning hundreds of times each second with a steadiness that is almost difficult to accept as real. To understand why that steadiness matters, it helps to think about what spin means for a neutron star. An ordinary pulsar, newly born from a supernova, carries enormous rotational energy, but it bleeds that energy slowly into space. The magnetic field drags against the surrounding environment, and the star loses momentum, fraction by fraction, year by year. This is called spin down, and it is not random. It follows a curve that astronomers can measure with great precision. By watching how quickly a pulsar slows, they can calculate roughly how long it has been spinning. They can estimate the strength of its magnetic field. They can read, in the rate of that deceleration, something like a biography. A young pulsar spins fast and slows quickly. An older one turns more slowly, more gently, its field weakened by time. The spin down is a kind of clock in itself, not counting forward, but counting backward toward the moment of birth. And then there are the ones that were given back their spin, the millisecond pulsars. They do not fit the ordinary biography. They are old, their magnetic fields quiet and diminished, and yet they rotate at speeds that newly born pulsars rarely reach, somewhere between roughly 100 rotations per second and up in the most extreme cases, more than 700 rotations per second. It is worth staying with that number for a moment, not to be startled by it, but to let it settle quietly into the mind. 1 rotation per second is already fast for something the size of a city. 30 rotations per second, like the Crab pulsar, is extraordinary. But 700? The fastest millisecond pulsar we have found is known by its catalog designation, PSRJ 1748-2446 AD. It completes 716 full rotations every second. Every single second, without pause, without variation, without rest, 716 times around. And because it is a neutron star, dense beyond ordinary reckoning, roughly 20 kilometers across, the surface at its equator is not simply rotating in some abstract sense. It is moving, physically moving through space at roughly 24% of the speed of light. A quarter of the speed of light. At the equator of that star, the surface is traveling at something close to 72,000 kilometers per second. Not the whole star, just the skin of it. The outermost layer, tracing its circle 700 times in the span of a single breath. There is no material process on Earth that approaches this. No engineered object. No natural phenomenon at human scales. The comparison simply runs out of useful reference points, and so it is perhaps better to let it rest as it is. A star, old and quiet in its way, turning in the dark at a speed that belongs to a different order of physical reality than the one we inhabit. How does something reach that speed? Not through the violence of its birth. A freshly collapsed neutron star does spin rapidly, but not like this. The millisecond pulsars arrive at their extraordinary rotation through a different path entirely. A slower path, and in some ways, a stranger one. They begin as ordinary neutron stars. They slow over millions of years, as all pulsars do. Their magnetic fields weaken, their pulses fade. In many cases, they would eventually become undetectable, quiet remnants drifting through the galaxy without announcement. But some of them are not alone. Some neutron stars exist in binary systems, paired with another star, orbiting each other across a gravitational bond that can persist for billions of years. And when that companion star ages and expands, as stars eventually do, something begins. Matter flows. The outer layers of the companion drift toward the neutron star, drawn by its gravity. They do not fall straight down. They spiral inward, forming a flattened disk of gas that circles the neutron star before gradually descending to its surface. And as that matter falls, it carries angular momentum with it. It pushes, gently, continuously, over timescales almost too long to hold in the mind. This process, accretion, astronomers call it, does not happen quickly. It takes hundreds of millions of years. Hundreds of millions of years of matter falling, spinning, transferring its momentum to the neutron star below, and the neutron star, patient and dense and almost impossible to disturb, absorbs that momentum and spins faster and faster and faster still, until it reaches speeds that its youth never gave it. This is why they are called recycled pulsars. It is a word that carries something true in it. These are not young objects full of the energy of creation. They are old objects, transformed, given a second life by the long, slow generosity of a companion's gravity. They have been through something, a kind of stellar patience that has no human equivalent. The companion star, in most cases, does not survive the process unchanged either. By the time accretion ends, it has given away so much of its mass that it has become a white dwarf, a small, cooling remnant of what it once was. And so the two objects continue orbiting each other, the white dwarf, quiet and fading, the millisecond pulsar, spinning at speeds that seem to belong to a younger universe. There is a kind of tenderness in that image, if you allow it. Two old things circling each other in the dark, one having given something essential to the other carrying that gift forward, turning with it for billions of years. The spin down of a millisecond pulsar is almost imperceptibly slow. Because its magnetic field is so much weaker than a young pulsar's, the braking force is minimal. These stars lose their rotation so gradually that some of them will still be spinning hundreds of times per second long after the sun has exhausted its fuel and gone quiet. They are, in a real sense, among the most persistent things in the universe. And that persistence is not merely a curiosity, it is useful. Because a star that spins with such regularity, that loses so little of its speed over such long stretches of time, is in effect a clock. Not a metaphorical clock, a clock in the most precise sense of the word, something that marks equal intervals of time with extraordinary fidelity. The best atomic clocks on Earth keep time by counting the oscillations of cesium atoms. They are accurate to about 1 second in 300 million years. That is a precision almost beyond imagining at human scales. And yet some millisecond pulsars match it. Some exceed it. Their pulses arrive at radio telescopes with a regularity that, over decades of observation, deviates by only a few hundred nanoseconds. A nanosecond is 1/1000th of a second. The deviation, accumulated over years, is smaller than the blink of any eye, smaller than the fastest nerve impulse, smaller than almost any interval that has meaning in ordinary life. A dead star, spinning in the dark, keeping better time than the finest instruments human hands have made. There is something in that worth carrying into sleep. Not the strangeness of it, not the numbers, but the quieter thing underneath them. The idea that precision does not require intention, that regularity can emerge from violence and age and the slow pull of gravity across hundreds of millions of years, that the universe, without trying, without knowing, produces something that ticks, and ticks, and ticks. That ticking did not come easily. It was earned, across a span of time so long that the word long barely applies. To understand how a millisecond pulsar comes to spin so fast, it helps to picture what came before. A neutron star, already ancient by the time the story begins, it formed in a supernovae, spun quickly in its youth, and then gradually slowed. Decades passed, centuries, millions of years. The star dimmed and quieted, its rotation winding down the way a top winds down when no one is there to keep it spinning. But some neutron stars are not alone. Some orbit a companion, another star, close enough that gravity becomes a kind of conversation between them. And when that companion star ages and expands, as stars do, its outer layers begin to spill across the space between them. Slowly at first, then in a steady, curving stream. That infalling matter does not fall straight down. It spirals. It forms a flattened disk around the neutron star, a structure called an accretion disk, and as the material spirals inward, it heats. It heats to temperatures that produce not just light, but X-rays. The system blazes across the sky in wavelengths the human eye cannot see. A bright and violent pairing that astronomers call an X-ray binary. For hundreds of millions of years, matter rains down onto the neutron star's surface, and with each particle that arrives, it carries a small gift of angular momentum, a tiny push, a nudge toward faster rotation. One nudge means nothing, but hundreds of millions of years of nudges, that is something else entirely. Gradually, almost imperceptibly, the old neutron star begins to spin faster, faster than it ever spun in its youth, faster than any ordinary pulsar, until it is rotating not once per second, not 10 times per second, but hundreds of times per second, a dead star reborn through the slow patience of accumulation. This is why astronomers sometimes call them recycled pulsars. The name is quiet and apt, not created anew, but given back something they had lost, returned to motion by a process that took longer than the Earth has existed. Eventually, the companion star exhausts itself. The flow of matter slows and stops. The accretion disk fades. What remains is a neutron star spinning at extraordinary speed, and beside it, the dim remnant of its companion, a white dwarf, cooling slowly in the dark. The two of them orbit each other in silence, the white dwarf a pale witness to what it helped create. And now the recycled pulsar pulses again. Its radio beams sweep through space with each rotation, arriving at our telescopes hundreds of times every second. But there is something different about these pulses compared to those of younger pulsars, something that took physicists time to fully appreciate. The magnetic field is weaker. Young pulsars carry magnetic fields of almost incomprehensible strength, roughly 1 trillion times stronger than Earth's own field. But over the long accretion process, something happens to that field. It is thought to decay or to be buried beneath the infalling matter, or both. The precise mechanism is still a matter of careful study. What is clear is the result. A millisecond pulsar's magnetic field is far weaker than a young pulsar's, perhaps 1,000 times weaker or more. And that weakness is, in a quiet way, a gift. A strong magnetic field is a powerful brake. It couples the spinning star to the surrounding space, radiating energy, slowing the rotation. A weaker field means less braking, less energy lost with each turn. The star spins on and on, its rotation barely disturbed, decade after decade, century after century. This is the physical foundation of the millisecond pulsar's extraordinary stability. Not just that it spins fast, but that it spins consistently, that the interval between one pulse and the next remains almost perfectly constant across years of observation, that the clock, once wound, does not easily run down. Consider what that means in practice. Astronomers point a radio telescope at a millisecond pulsar and record the arrival time of each pulse. They do this not once, but thousands of times, over years, over decades. They build a timing model, a precise mathematical description of when each pulse should arrive, accounting for the pulsar's rotation, its position in the sky, its motion through space, the motion of the Earth around the Sun. And then they compare the model to the measurements. The difference between predicted arrival time and actual arrival time is called the timing residual. For a well-behaved millisecond pulsar, those residuals are extraordinarily small. Some pulsars, observed continuously for more than 20 or 30 years, show timing residuals of only a few hundred nanoseconds. A nanosecond is 1/1,000,000th of a second. A few hundred nanoseconds, accumulated over decades, is a deviation so small it is difficult to place in any human context. It is smaller than the time it takes light to cross a room, smaller than the fastest signal the human nervous system can carry, a dead star. spinning in the dark across hundreds or thousands of light years, keeping time to within a few hundred billionths of a second over the span of a human career. The comparison to atomic clocks is not rhetorical. Atomic clocks, the kind that define the international standard of time, work by counting the oscillations of cesium atoms. A cesium atom, when stimulated in a particular way, oscillates at a frequency of just over 9 billion cycles per second. That frequency is extraordinarily stable, and by counting those oscillations, an atomic clock can keep time to about 1 second in 300 million years. That is the benchmark. 300 million years without losing a second. And some millisecond pulsars approach it. Some, over the spans we have been able to observe them, appear to match it. A few may even exceed it, though the comparison is complicated by the fact that we have only been watching for decades, not millennia, and the full picture of their long-term stability is still being assembled. What is certain is that they belong in the same conversation. A human technology refined over generations of careful physics, counting the trembling of individual atoms in a shielded laboratory, in a remnant of stellar death, spinning in the interstellar dark, shaped by gravity and time and the slow rain of matter from a companion star, both keeping time, both arriving by entirely different paths, at the same extraordinary precision. There is no reason the universe should have provided this. No reason a dead star should spin so steadily. No reason the product of a supernova and hundreds of millions of years of accretion should happen to produce something useful to beings who would not exist for billions of years more. And yet the precision is there, waiting, whether or not anyone is listening. The pulsar does not know it is a clock. It simply spins. It simply pulses. It has been doing so, in some cases, since before the Earth formed, and it will continue long after every atomic clock ever built has been lost to time. There is something restful in that thought. Not the numbers, not the nanoseconds, but the image underneath them. A small, dense star, alone or nearly alone in the dark, turning with a patience and a regularity that asks nothing of anyone. Ticking, and ticking, and ticking. That steadiness, that deep, unhurried regularity has a physical reason behind it. It comes down to something called rotational inertia. When an object is spinning, it resists any change to that spin. The more massive it is, the more compact it is, the harder it becomes to slow it down or speed it up. A neutron star carries an almost incomprehensible amount of mass packed into a sphere roughly 20 kilometers across. The rotational inertia of such an object is enormous, far beyond anything we can build or replicate. Once it is spinning, almost nothing in the universe has the leverage to disturb it. Small forces act on it, of course. The magnetic field bleeds away energy slowly. The thin surrounding medium offers the faintest resistance. Over millions of years, the rotation does ease, very gradually. But on human timescales, on the timescale of a career, a lifetime, a civilization, a millisecond pulsar simply holds. It holds the way a gyroscope holds its orientation, but deeper, quieter, more absolute. And because it holds so steadily, it becomes possible to listen very carefully. Astronomers measure pulsar timing by recording the precise moment each pulse arrives at a radio telescope. Not the pulse itself, exactly. The shape of a pulse can vary slightly, but the arrival time, noted to within fractions of a microsecond, logged against an atomic clock on the ground, pulse after pulse, year after year. The record accumulates. What emerges from that record is a timing model, a mathematical description of the pulsar's rotation, its position in the sky, its distance, its motion through space. The model predicts when the next pulse should arrive, and then the next, and the one after that. Most of the time, the pulses arrive exactly when the model says they will. But sometimes, very slightly, they do not. And those tiny deviations, those small, quiet discrepancies between prediction and reality carry information. If a pulsar has a companion orbiting it, the pulsar itself moves in a small orbit around their shared center of mass. When the pulsar moves toward Earth, its pulses arrive a little early. When it moves away, they arrive a little late. The pattern repeats with the orbital period, and from that pattern, astronomers can read the companion's mass, the shape of the orbit, the tilt of the orbital plane. All of it encoded in the timing of a distant heartbeat. This is how the double pulsar was found, how binary systems have been mapped across the galaxy, how general relativity has been tested in conditions no laboratory could ever provide. And it is how something else was found, something that surprised nearly everyone. In 1992, an astronomer named Alexander Wolszczyn, working with Dale Frail, announced the discovery of planets orbiting a millisecond pulsar. The pulsar was designated PSR 1257+12, and it lay roughly 1,000 light-years away in the constellation Virgo. The timing residuals had revealed two clear periodic signals, two companions, orbiting the pulsar with periods of roughly 67 and 98 days. Their masses were comparable to Earth's. They were, by any reasonable definition, planets. They were also the first confirmed planets ever found beyond our solar system. Not orbiting a sun-like star, not in a system that resembled our own, but circling a dead star, a remnant of catastrophe, in a bath of radiation so intense that any atmosphere would be stripped away almost instantly. There is something quietly unsettling about that. For decades, the search for other worlds had assumed they would be found in places something like home, around warm, stable stars, in conditions that might permit life as we understand it, and the first confirmed answer came from the most hostile environment imaginable. The pulsar planets of PSR 1257+12 almost certainly bear no resemblance to Earth. No air, no water, no shelter from the relentless radiation pouring from the star at their center. They are, as far as we can tell, bare and irradiated and silent. And yet they orbit. They persist. They were there, quietly tracing their paths for the entire history of human civilization, and long before it, waiting to be noticed by the slight irregularity they pressed into a pulsar's timing. There is a third, smaller body in that system as well, roughly the mass of the Moon, orbiting much closer. Its signal is fainter, harder to extract from the noise, but it is there. A pulsar with a small family of worlds. The universe is stranger and more varied than the imagination tends to reach for on its own. And the method that found those planets, patient, precise, listening for the faintest deviation in an otherwise perfect rhythm, turns out to have an even larger application. If a single pulsar can be used as a clock, a network of pulsars can be used as something far more ambitious. Spread across the sky, dozens of millisecond pulsars tick away simultaneously, each one monitored by radio telescopes on the ground, each one accumulating years of timing data, each one a node in what astronomers call a pulsar timing array. The idea is this: gravitational waves, ripples in the fabric of space-time itself, stretch and compress the distances between objects as they pass. When a gravitational wave moves through the space between Earth and a pulsar, it very slightly changes the time it takes for each pulse to arrive. The change is extraordinarily small, a fraction of a microsecond, spread over months or years. No single pulsar could reveal this on its own. The signal would be lost in the noise of measurement, in the small irregularities of the interstellar medium, in the limits of any individual clock. But if the same gravitational wave passes through the positions of many pulsars at once, it leaves a correlated pattern across all of them. Pulses arriving slightly early here, slightly late there, in a way that reflects the geometry of the wave itself. By comparing the timing residuals of dozens of pulsars simultaneously, pulsars separated by thousands of light years, astronomers can detect gravitational waves with wavelengths measured not in kilometers, but in light years. The instrument has no physical structure, no mirrors, no arms, no cables connecting its parts. It is assembled entirely from light and time and the patient rotation of dead stars. Its baseline, the distance between its outermost components, is a significant fraction of the galaxy itself. Nothing built by human hands comes close. And what this instrument listens for is not the sharp, brief chirp of two stellar mass black holes colliding, the kind of event LIGO was built to catch, but something slower, deeper, more pervasive. A low hum of gravitational waves washing through the universe continuously, produced by pairs of supermassive black holes in distant galaxies, each pair containing millions or billions of solar masses, slowly drawing together over millions of years. The background murmur of the largest gravitational events in the observable universe. Encoded, faintly, in the arrival times of pulses from spinning neutron stars. There is a particular quality to this image that is worth resting with for a moment. A star died. Its core collapsed in less than a second. What remained was a neutron star, dense beyond easy comprehension, spinning in the dark. Over hundreds of millions of years, a companion star slowly fed it matter, spinning it faster and faster until it reached hundreds of rotations per second. The companion faded to a white dwarf. The pulsar settled into its rhythm. And now, billions of years later, the faint radio whisper of that rotation reaches a dish on the surface of a small planet and carries within its timing the signature of black holes merging in galaxies so distant their light has been traveling since before the Earth existed. One dead star, listening, in its way, to the slow collision of objects a billion times its mass. Across distances the mind cannot hold. And what makes this possible is something almost delicate in its simplicity. A gravitational wave passing through the galaxy does not announce itself loudly. It does not shake the ground or bend visible light. It does something far quieter. It stretches and compresses the fabric of space itself, very slightly, as it moves through. And when it passes between Earth and a distant pulsar, the distance between them changes, just a little, by an amount far smaller than the width of an atom. But the pulsar is still ticking, hundreds of times every second, with the patience and precision of something that has been doing this for billions of years. And so that tiny change in distance shows up as a tiny change in when the pulse arrives. A pulse that should reach the telescope at a certain moment arrives a few nanoseconds early or a few nanoseconds late. That is the signal. A whisper inside a whisper. A single pulsar cannot tell you much on its own. One clock running slightly fast or slightly slow could mean almost anything. A small irregularity in the pulsar itself, a slight miscalculation in the model, the faint tug of an unseen companion. There are many reasons a single pulse might arrive a heartbeat off from where it was expected. But here is where the method becomes something remarkable. If a gravitational wave is moving through the galaxy, it does not affect just one pulsar. It affects all of them at once, in a pattern. Pulsars in certain directions across the sky will have their pulses arrive slightly early. Pulsars in other directions will arrive slightly late. The pattern of these deviations, which astronomers call timing residuals, follows a specific mathematical shape that is the signature of a gravitational wave, and nothing else. So astronomers do not listen to one pulsar. They listen to many, spread across the sky like points of a vast, invisible net. And they look for the moment when all those tiny deviations begin to move together, correlated, in the way that only a wave passing through the whole galaxy could produce. This is the pulsar timing array. Not a single telescope, not a single dish pointed at a single star, but a network of millisecond pulsars, each one a node in an instrument whose scale is almost impossible to hold in the mind. The baselines of this detector are not measured in meters, or kilometers, or even light seconds. They are measured in thousands of light years. The pulsars themselves are the detector scattered across the Milky Way, ticking in the dark, each one a reference point in a web of time that spans the galaxy. One of the largest efforts to build and maintain this web is based in North America. The North American Nanohertz Observatory for Gravitational Waves, known as NANOGrav, monitors roughly 70 millisecond pulsars, each one observed regularly. Its pulse arrival times recorded with care, its timing model refined year by year. 70 dead stars, spinning in the dark, each one a thread in the same listening instrument. And NANOGrav is not alone. Similar projects have been running in parallel across the world. In Europe, a collaboration of radio observatories has been building its own Pulsar timing array for years. In Australia, astronomers have been monitoring their own set of southern sky pulsars, reaching stars invisible from the northern hemisphere. In India and in China, large radio telescopes have joined the effort, adding their own carefully timed observations to the growing record. Each project sees a different part of the sky. Each one listens to different pulsars, and each one accumulates years of data, pulse by pulse, nanosecond by nanosecond. The data from all of these collaborations is brought together under a single framework called the International Pulsar Timing Array, a quiet coordination of observatories spread across 5 continents, all listening to the same low hum, all trying to hear the same thing. And in 2023, they heard it. Not all at once, and not with absolute certainty. Science rarely arrives that cleanly, but multiple pulsar timing array collaborations, working independently with their own data, announced strong evidence for something that had been predicted but never before confirmed: a gravitational wave background, a low, pervasive hum of gravitational waves filling the galaxy, not from a single source, not from one dramatic event, but from countless sources all at once, their waves overlapping and blending into something continuous. The announcement was careful, as these things should be. The word used was evidence, not proof. The signal was consistent with what had been predicted, and it was present across multiple independent datasets, which gave it weight. But the work of confirming and characterizing it continues, as it will for years to come. What is thought to be producing this background is the slow, patient violence of the largest structures in the universe. Across the observable cosmos, there are galaxies, hundreds of billions of them. And at the center of most large galaxies sits a supermassive black hole, an object containing millions, or hundreds of millions, or in some cases billions of times the mass of the Sun, compressed into a region smaller than our solar system. Galaxies collide. It happens slowly, over hundreds of millions of years, but it happens. When 2 galaxies merge, their central black holes do not simply pass through each other. They sink toward the center of the merged galaxy. They find each other. They begin to orbit. And then, over immense stretches of time, they spiral inward, losing energy to the surrounding stars and gas, drawing closer, until eventually they are close enough that gravitational wave emission itself carries away the remaining energy and pulls them together. Each such pair, in its long spiral, it radiates gravitational waves, not the sharp, brief chirp of 2 stellar mass black holes colliding in a fraction of a second, but a slow, deep oscillation that takes years, sometimes decades, to complete a single cycle. The frequency is so low, it has no analog in sound that a human ear could register. These are nanohertz waves, a billion times lower in frequency than the waves LIGO detects. And there are so many of these pairs, in so many galaxies, at so many different stages of their long approach, that their waves overlap into a background, a gravitational hum that fills the universe the way background light fills the night sky, present everywhere, at all times, in all directions. That is what the pulsar timing arrays are hearing. The slow merging of the largest objects the universe has ever made, translated into nanosecond shifts in the arrival times of pulses from spinning neutron stars, detected by a network of radio dishes spread across a single small planet, orbiting an ordinary star, in one unremarkable corner of one galaxy among hundreds of billions. There is something very still about this, if you let it settle. The gravitational wave background has been moving through the galaxy for longer than the Earth has existed. It was there before the first human looked up at the night sky. It was there before the first radio telescope was built. It was there, passing silently through everything, carrying the record of collisions so vast and so distant that no other signal from them will ever reach us. And we found it, not by building something larger than the universe, but by listening carefully to the clocks it had already placed there. Dead stars, spinning in the dark, patient beyond any human measure, keeping time through everything. There are two kinds of gravitational wave detectors in the world right now, and they listen to entirely different registers of the universe. LIGO, the Laser Interferometer Gravitational Wave Observatory, listens for the brief, sharp collisions of stellar mass black holes. Two black holes, each perhaps 10 or 30 times the mass of the Sun, spiraling together and merging in a fraction of a second. The gravitational wave from that event arrives at Earth as a ripple that oscillates hundreds of times per second. It lasts less than a breath, and then it is gone. Pulsar timing arrays listen for something else entirely. The waves they detect oscillate not hundreds of times per second, but roughly once every several years. Their frequency is measured in nanohertz, billionths of a hertz. A single oscillation of one of these waves takes longer than a human childhood, longer, in some cases, than the entire span of recorded history. These are not the same phenomenon at different volumes. They are genuinely different kinds of disturbance, produced by genuinely different kinds of event. LIGO hears the sharp crack of two small, fast objects colliding. Pulsar timing arrays hear the long, slow groan of the largest gravitational systems the universe contains, supermassive black holes, each billions of times the mass of the Sun, taking millions of years to complete a single orbit around each other. The frequency difference between these two kinds of wave is roughly 1 billion times. That is not a small gap. It is the difference between a sound you could hear in a room and a vibration so slow that the room itself would have to be the size of a galaxy to contain one full cycle. And yet both are gravitational waves. Both are ripples in the fabric of space-time, predicted by the same equations Einstein wrote down in 1915. The universe expresses the same underlying physics across a range so vast it is almost impossible to hold in mind. Almost. Let the thought rest there for a moment. There is a place in the sky, in the constellation Puppis, where two pulsars orbit each other. This system is called PSR J0737-3039. It was discovered in 2003, and it remains the only known system in which both members of a binary pair are active pulsars. Both are spinning, both are beaming, both are ticking, and both are falling, very slowly, toward each other. They orbit their common center of mass roughly once every 2.5 hours. At their closest approach, they are separated by less than the distance from Earth to the Moon. Two neutron stars, each roughly 20 kilometers across, each containing more mass than the Sun, separated by a gap a human spacecraft could cross in a few days. The system is a laboratory that no human hand could ever build. General relativity makes very specific predictions about what happens in a system like this. As the two pulsars orbit, they emit gravitational waves. Those waves carry energy away from the system, and as energy is lost, the orbit shrinks. The two stars spiral, imperceptibly slowly, toward each other. This is called orbital decay. Einstein's equations predict exactly how fast that decay should proceed, given the masses of the two stars and the geometry of their orbit. And the measured decay matches those predictions to better than 99.99% accuracy. That number deserves a moment of quiet. 99.99%. Across a system of two dead stars orbiting each other at a fraction of the speed of light, in conditions no laboratory on Earth could approach, the theory holds. It holds with a precision that is almost unsettling in its completeness. This is not the first time pulsars have confirmed general relativity. The binary pulsar PSR 1913+16, discovered in 1974, provided the first indirect evidence for gravitational waves through exactly this kind of orbital decay measurement. That work earned the Nobel Prize in Physics in 1993, PSR J0737-3039 refined the test further, with 2 pulsars instead of 1, offering more data, more constraints, more ways for the theory to fail. It did not fail. There is something quietly reassuring about this. The universe, in its most extreme environments, still follows the rules. The same equations that describe the bending of light around the sun, the same equations that make GPS satellites require tiny timing corrections, the same equations written by a man working at a desk in Berlin more than a century ago. They hold, precisely, around 2 spinning neutron stars falling toward each other in the dark. Every pulse a pulsar sends toward Earth carries more than just a timestamp. It carries a record of everything it passed through on the way. Between any pulsar and Earth lies the interstellar medium, the thin, diffuse material that fills the space between stars. It is not empty. It contains gas, dust, magnetic fields, and free electrons. Electrons that have been stripped from their atoms by the radiation of nearby stars and left to drift, loosely, through the galaxy. When a radio pulse travels through this sea of free electrons, the electrons slow it down, and they do not slow all frequencies equally. Lower frequency radio waves are slowed more than higher frequency ones, so a pulse that began as a sharp, simultaneous burst of many frequencies arrives at Earth slightly smeared, the lower frequencies trailing behind the higher ones by a small but measurable amount. This effect is called dispersion. The amount of dispersion in a pulse depends on how many free electrons the pulse passed through on its journey. A pulsar that is farther away, or that lies along a line of sight passing through denser regions of ionized gas, will show more dispersion. A pulsar that is nearby, or that sits in a relatively clear corridor of space, will show less. By measuring the dispersion of pulses from hundreds of pulsars scattered across the sky, astronomers can build a 3-dimensional map of the free electron density throughout the galaxy. They can trace the spiral arms, where star formation is active and ionized gas is plentiful. They can find the quieter regions between the arms, where the interstellar medium is thinner and clearer. The galaxy, in this way, becomes legible, not through direct imaging. The distances involved are far too great for that, but through the patient accumulation of tiny delays in the arrival times of pulses from dead stars. Each pulsar is a probe that has already been placed by the physics of stellar evolution at a specific location in the galaxy. It has been transmitting continuously, in some cases for billions of years. All we have to do is listen and measure and compare. The dispersion measure of a pulsar, a single number, derived from the frequency-dependent delay in its pulses, encodes the column of ionized gas between that pulsar and Earth. Thousands of such measurements, taken together, reveal the large-scale structure of the interstellar medium with a clarity that no other method can match. There is something meditative about this process. The pulsar does not know it is being used as a probe. It simply spins and pulses and sends its signal outward in all directions. The interstellar medium does not know it is being mapped. It simply exists, diffuse and ancient, filling the spaces between the stars. And somewhere on a small planet, a radio dish turns slowly to follow a point of sky and records the arrival of a pulse that left its source perhaps 1,000 years ago, and notes, with great care, exactly how late the low frequencies arrived. And from that delay, a small piece of the galaxy becomes a little more known. Most pulsars announce themselves through radio waves alone, a single narrow band of the electromagnetic spectrum, patient and precise. But some pulsars speak in many languages at once. Radio waves are only the beginning for certain neutron stars. They also emit X-rays, streaming outward from the heated regions near the poles, gamma rays, carrying energies millions of times greater than visible light, and in rare cases, something quieter and stranger, actual visible light, faint enough to require the largest telescopes on Earth to detect. A neutron star producing visible light. There is something almost impossible about that image. An object 20 kilometers across, the collapsed remnant of a star that once dwarfed the sun, glowing faintly enough to be seen, not just heard, not just measured in radio frequencies, but seen across thousands of light years of space. The most studied example of this is a pulsar that has been known, in one form or another, for nearly 1,000 years. In the summer of 1054, astronomers in China recorded the appearance of a new star in the sky. It was bright enough to be visible in daylight for several weeks. It faded slowly over the following months and eventually disappeared from view. What those observers were watching was a supernova, the death of a massive star, roughly 6,500 light-years away. What they could not have known was what remained at the center of that explosion. Today, we call it the Crab Pulsar. It rotates 30 times every second. Not the fastest pulsar we know of, but fast enough that its rotation is measurable not just in radio waves but across the entire electromagnetic spectrum. X-rays, gamma rays, optical light, radio, all of them pulsing in lockstep, 30 times per second as the star turns. The Crab Pulsar is young. As pulsars go, roughly 1,000 years old. And youth, in a neutron star, means energy. It has not yet had the billions of years of quiet spin-down that soften older pulsars into the precise, gentle timekeepers we use for gravitational wave detection. It is still loud, still radiating intensely, still pushing its energy outward into the surrounding space. And that energy has not gone unnoticed. Around the Crab Pulsar lies the Crab Nebula, the expanding shell of gas and dust thrown outward by the original supernova. It stretches across roughly 11 light-years of space now, still growing, still moving outward at about 1,500 kilometers per second. But the nebula is not simply coasting on the momentum of that ancient explosion. It is still being fed. The Crab Pulsar drives a wind of charged particles outward from its surface, electrons and positrons moving at a significant fraction of the speed of light. This pulsar wind slams into the surrounding nebula, transferring energy continuously, keeping the gas glowing. The intricate filaments and knots of light visible in images of the Crab Nebula are not echoes of a past event. They are the present tense output of a star that died 1,000 years ago and has not stopped working since. There is something quietly relentless about that. A star exhausts its fuel, collapses, explodes, and leaves behind a spinning remnant 20 kilometers across. And that remnant continues to illuminate its own grave, decade after decade, century after century, with no sign of stopping for thousands of years to come. Not all neutron stars settle into the steady, measurable rhythm of a pulsar. Some take a different path entirely. Magnetars are a subclass of neutron stars defined by their magnetic fields. Ordinary pulsars already have magnetic fields roughly 1 trillion times stronger than Earth's. Magnetars exceed even that by a factor of about 1,000. Their fields are so intense that they distort the very shape of atoms near the surface, stretching electron clouds into elongated forms that bear little resemblance to the atoms we encounter in ordinary matter. These fields do not simply sit quietly. They store enormous amounts of energy, and occasionally they release it. A magnetar flare is among the most energetic events that can occur in the known universe on short timescales. In a fraction of a second, a magnetar can release more energy than the sun emits over tens of thousands of years. The mechanism involves the sudden fracturing or rearrangement of the magnetic field, a kind of starquake, though the analogy only goes so far because nothing on Earth produces energy on remotely this scale. In December of 2004, a magnetar designated SGR 1806-20 released a flare of this kind. It lasted only a fraction of a second at its peak, and it was energetic enough to measurably ionize the upper atmosphere of Earth from a distance of roughly 50,000 light-years. That distance is worth sitting with for a moment. 50,000 light-years is more than halfway across the Milky Way. The light and radiation from that flare had been traveling for 50,000 years before it reached us, and when it arrived, it was still powerful enough to alter the chemistry of our atmosphere, briefly and measurably, as if a switch had been thrown somewhere in the upper sky. No harm came to the surface of the Earth. The atmosphere absorbed what arrived, but the instruments that monitor ionospheric conditions registered the event clearly, and for a moment, a dead star 50,000 light-years away had left a faint fingerprint on the air above us. The universe is not always as distant as it seems. Returning to the pulsars that tick with such extraordinary regularity, even they are not perfectly steady. Every so often, a pulsar will glitch. A glitch is a sudden, small increase in a pulsar's rotation rate, not a slowdown, but a brief speed up, happening in a matter of seconds or less, followed by a gradual return toward the previous spin rate over days or weeks. These events are subtle. The change in rotation rate is typically a fraction of a millionth of a percent, but they are real, and they are detectable, and they carry information about what lies beneath the crust. The leading explanation involves the interior of the neutron star. Below the iron crust, the neutron star is thought to contain a layer of superfluid neutrons. A superfluid is a state of matter in which particles flow without any friction whatsoever. On Earth, superfluidity can be achieved in certain materials cooled to temperatures near absolute zero, and it produces striking effects: liquids that climb the walls of containers, that flow through microscopic gaps without resistance. But the superfluid inside a neutron star exists under conditions of pressure and density that no laboratory can replicate. This superfluid does not spin in the same way the crust does. It maintains its own rotation, somewhat independently, threaded through with tiny vortices that carry the angular momentum of the fluid. Over time, as the crust slows down through normal spin down, a difference builds up between the rotation of the crust and the rotation of the superfluid beneath it. And then, suddenly, that difference resolves. Angular momentum transfers from the superfluid to the crust in a rapid cascade. The crust speeds up slightly, and the pulsar glitches. It is a window into a kind of matter that exists nowhere else. A superfluid core, spinning in the dark inside a star 20 kilometers across, occasionally nudging the surface just enough for us to notice from thousands of light years away. The pulsar does not know it is telling us anything. It simply spins and occasionally lurches forward by the smallest imaginable amount, and then settles back into its patient rhythm. And we, listening carefully across the light years, write down the time. And yet, even the glitch is only the surface of the mystery. What lies beneath the crust, beneath even the superfluid layer, is something physics has not yet fully resolved. Go deeper into a neutron star, and the pressure climbs beyond anything we can describe with certainty. The density increases until neutrons are packed so tightly together that the very concept of individual particles begins to blur. And here, in the innermost core, some models suggest that neutrons may no longer exist as neutrons at all. They may dissolve, not into nothing, but into something more fundamental, into quarks, the smaller constituents that neutrons are built from. Under ordinary conditions, quarks are always bound together, confined inside protons and neutrons, never found alone. But at the densities thought to exist in the core of a neutron star, that confinement may break down. The quarks may move freely through the core, forming a state of matter called quark matter, dense, strange, and unlike anything that has ever existed in a laboratory. As far as we can tell, this has never been confirmed. It remains a possibility, written into certain equations, suggested by certain models, but not yet proven. The core of a neutron star is simply too small, too distant, and too hidden for us to observe directly. We cannot send anything there. We can only infer. And the inference depends on something called the equation of state. This is the relationship between the pressure inside a neutron star and its density, a kind of mathematical description of how the matter behaves under those extreme conditions. If you know the equation of state, you can calculate how large a neutron star of a given mass should be, how stiff or soft its interior is, whether it can support quark matter at its core or not. The equation of state of neutron star matter is one of the genuinely open problems in nuclear physics. There are many proposed versions of it. They make different predictions. Some suggest neutron stars should be relatively compact, perhaps 12 kilometers across. Others allow for larger stars, 15 kilometers or more. The difference matters enormously for understanding what neutron stars are made of and how matter itself behaves at its most extreme. For a long time, we had very few ways to measure it. And then, on the 17th of August, 2017, two neutron stars collided. They had been orbiting each other for perhaps 1 billion years, slowly losing energy to gravitational waves, their orbit tightening by imperceptible amounts with each passing year. And then, in the final moments, the in-spiral accelerated. The two stars drew closer and closer, faster and faster, until they met. The collision lasted milliseconds. In that brief time, gravitational wave detectors on Earth, LIGO in the United States, and Virgo in Italy, recorded the signal of the merger, a chirp in space-time, rising in frequency as the stars spiraled inward, then a final burst as they collided. The event was cataloged as GW170817. It was the first neutron-star merger ever detected in gravitational waves. And within seconds, telescopes around the world turned toward the source, because this merger was also visible in light, in gamma rays first, then in ultraviolet, then in optical wavelengths, then infrared and radio. Astronomers watched it brighten and fade over days and weeks, gathering data from across the electromagnetic spectrum. What they saw confirmed something that had long been theorized but never directly observed. The merger produced a kilonova. A kilonova is a particular kind of explosion, not as violent as a supernova, but extraordinary in its own way. When two neutron stars collide, the neutron-rich debris ejected from the collision undergoes a rapid cascade of nuclear reactions. Neutrons are captured by atomic nuclei faster than those nuclei can decay, building up heavier and heavier elements in a matter of seconds. This process, called the R process, for rapid neutron capture, is one of the primary ways the universe forges elements heavier than iron. Gold is one of them. Platinum is another. And uranium, and lead, and dozens of other heavy elements that cannot be made inside ordinary stars. They require the extreme neutron flux of a neutron star merger, the brief and violent abundance of free neutrons that exists nowhere else. The light from GW170817 carried the spectral signatures of these elements. Astronomers identified strontium in the kilonova's glow, and the overall brightness and color of the explosion was consistent with the production of a substantial amount of gold and platinum, perhaps several times the mass of Earth, forged in those few seconds of collision. It is a quiet thing to sit with. The gold in a ring, or in the contacts of an old electronic device, or simply in the ground beneath a mountain somewhere. That gold was not made in the sun. It was not made in any star that burned steadily for billions of years. It was made in a collision, in a moment of extraordinary violence, in the debris of two dead stars that had been circling each other in the dark for longer than the Earth has existed. And then it scattered. The kilonova's ejecta expanded outward into space, cooling, dispersing, eventually mixing with the gas and dust of the surrounding galaxy. Over millions of years, that enriched material drifted and condensed. Some of it found its way into the molecular cloud that would eventually collapse to form our solar system, roughly 4.5 billion years ago. And some fraction of that, a small fraction, but a real one, became the Earth, became the crust beneath the continents, became the veins of ore that human beings would one day mine. The gold on this planet is old in a way that is difficult to hold in the mind. It predates the sun. It predates the Earth by hundreds of millions of years, perhaps more. It was forged in a neutron star merger that occurred somewhere in the Milky Way long before our solar system existed, in a collision that no one witnessed, that left no record except the elements themselves. And GW170817 gave us the first direct evidence that this is how it happens. The gravitational wave signal also carried information about the neutron stars themselves, their masses, the way they deformed as they approached each other, the stiffness of their interiors. This data has been used to constrain the equation of state, to narrow down the range of possibilities, to rule out some of the more extreme models and favor others. The neutron stars in that merger appear to have been relatively compact, suggesting a moderately stiff equation of state, though the constraints are still being refined. Each new merger detected will add another measurement. Each one will tighten the picture a little more. We are, slowly and carefully, learning what the inside of a neutron star is made of, not by going there, but by listening to the gravitational waves that ripple outward when two of them finally meet. The universe does not offer easy answers, but it does, occasionally, offer a collision, a brief and brilliant moment when two patient, ancient objects end their long silence and tell us something about the nature of matter itself. And we are here at just the right moment in history, with just the right instruments to hear it. And yet, for all that we have heard so little. As of the mid-2020s, astronomers have cataloged roughly 3,000 pulsars, 3,000 points of light in the dark, each one a spinning neutron star, each one ticking away in its own quiet corner of the galaxy. It sounds like a large number. And in one sense, it is. Each detection represents years of careful observation, careful timing, careful work. But the Milky Way is estimated to contain over 100,000 active pulsars. 100,000. We have found perhaps 3 in every 100. The rest are out there, spinning in silence, their beams sweeping through space in directions that never quite reach us. Some are simply too far away, their signals thinned to nothing by the vast distances between stars. Others are pointed elsewhere, their lighthouse beams rotating through arcs that miss Earth entirely, as they have missed Earth for millions of years, as they will continue to miss it long after we are gone. This is one of the quieter truths about the universe, that most of what exists is not visible to us, not because it is hidden, exactly, but because the geometry does not favor us. A pulsar does not know we are listening. It does not aim its beam toward us. It simply spins, and we happen to be in the way, or we are not. Most pulsars, we are not in the way of, and so they tick on, undetected, uncatalogued, unnamed, patient and precise in the dark. But that is beginning to change. In the plains of South Africa and the outback of Western Australia, something is being built. The square-kilometer array, a radio telescope unlike anything constructed before, not a single dish, but thousands of them spread across 2 continents, their signals combined into an instrument of extraordinary sensitivity. When complete, it will have a total collecting area of roughly 1 square kilometer, enough to detect radio signals of a faintness that current telescopes cannot reach. Astronomers expect it to discover tens of thousands of new pulsars. Tens of thousands. The catalog that took decades to build to 3,000 may grow by an order of magnitude within a few years of the array coming online. Pulsars that have been spinning undetected since before our civilization existed will suddenly announce themselves, their pulses arriving at the array's receivers for the first time. Each one a new clock, each one a new data point, each one a new window into the structure of the galaxy, the behavior of matter, the geometry of space. It is a slow kind of anticipation, the kind that does not rush, that simply waits for the instruments to be ready. And while we wait, there is another direction in which pulsars are beginning to be useful, not just for looking outward into the galaxy, but for finding our way through it. For a long time, spacecraft navigating through deep space have relied on signals from Earth. A radio transmission sent from a ground station bounced off the spacecraft, returned, the delay measured, the position calculated. It works, but it requires contact. It requires that Earth is reachable, that the signal can travel the distance and time, that someone is there to send it. The further a spacecraft travels, the longer that round trip takes, At the distance of Neptune, a signal takes roughly 8 hours to make the journey there and back. At the distances, we might one day send spacecraft to other stars, or simply to the far edges of our own solar system. The delay becomes impractical. There is another way. Pulsars are distributed across the sky in known positions. Their pulses arrive at predictable times that can be calculated in advance with great precision. If a spacecraft can measure the arrival time of pulses from several pulsars simultaneously, it can compare those measured times against the predicted times and determine its own position, not by asking Earth where it is, but by reading the sky directly. The principle is elegant in the way that the best ideas often are. The universe has already placed these clocks throughout the galaxy. We do not need to build them or maintain them or power them. We only need to listen. In 2018, a small instrument aboard the International Space Station demonstrated that this was not merely a theoretical possibility. NASA's NICER instrument, designed primarily to study neutron stars in X-ray light, was used to test pulsar-based navigation in practice. By timing the X-ray pulses from a set of known pulsars, the system was able to determine its position in space to within roughly 5 kilometers. 5 kilometers. In the context of deep space, where distances are measured in millions of kilometers, that is a remarkable result for an early demonstration. The technique will improve, the instruments will become more sensitive, the catalog of well-timed pulsars will grow, and one day, a spacecraft far from Earth may navigate not by radio contact with home, but by the quiet ticking of neutron stars scattered across the sky. There is something worth sitting with in that image. A small machine, alone in the dark between planets, orienting itself by listening to the remnants of stars that died billions of years ago, finding its place in the universe not by asking for help, but by reading the oldest, most reliable signals the cosmos offers. What makes this possible, what makes pulsars trustworthy enough to navigate by, is something called the pulse profile. Every pulsar has one. It is the shape of its average pulse, not any single pulse, which can vary slightly, but the average of thousands of pulses stacked together. That shape is stable. Remarkably, almost eerily stable. It persists not just over years of observation, but over millions of years of the pulsar's existence. The profile of a millisecond pulsar observed today will, as far as we can tell, be essentially the same profile it had long before Earth's continents were arranged as they are now. Each profile is also unique. No two pulsars produce the same shape. Some have a single smooth peak. Others have two peaks separated by a shallow valley. Others still have complex, multi-peaked structures that reflect the geometry of their magnetic fields and the precise angle at which their beam crosses our line of sight. These profiles are, in a very real sense, fingerprints, signatures that persist across cosmic time, stable enough to be used for identification across light years of space. This is what makes pulsar navigation possible, and it is what makes pulsar timing arrays possible. And it is, in a quieter way, what makes pulsars so unlike almost anything else we know of. Most things change. Stars brighten and dim. Planets shift in their orbits. Galaxies collide and reform over billions of years. Even atomic clocks, precise as they are, drift slightly over long enough timescales and must be corrected against each other. But a millisecond pulsar, spinning in the dark, maintains its rhythm with a patience that has no good comparison. It does not need to be wound or calibrated or checked. It simply spins and pulses and spins again. Its profile unchanged, its timing unwavering, its signal crossing the galaxy at the speed of light and arriving, after all that distance, still recognizable, still itself. There is a kind of peace in that. Some of these pulsars have been with us for a long time now. Not in the way a companion is with us, but in the way a lighthouse is, steady, indifferent, reliable. Astronomers have been tracking certain millisecond pulsars for more than 30 years, recording each pulse, logging each arrival time, slowly building what they call a timing model, a mathematical portrait of the pulsar's behavior, refined year by year, observation by observation. Each new measurement makes the model a little more precise. A small correction here, a slight adjustment to the orbital parameters there. Over decades, these models become extraordinarily detailed, accounting for the pulsar's spin-down rate, its proper motion across the sky, the gravitational influence of any companions, even the subtle warping of space-time along its line of sight. 30 years of listening. And the pulsar, for its part, has simply continued. It was spinning long before the first observation, long before the telescope that detected it was built, long before the astronomers who study it were born. A millisecond pulsar formed through the slow recycling process, accreted matter, spun up over hundreds of millions of years, may have been rotating at this same extraordinary rate for billions of years before any mind in the universe took notice. That is a difficult thing to hold. Billions of years of unwitnessed regularity, ticking away in the dark, in the silence between stars, with no one to receive the signal and no reason to send it. The pulsar does not know it is a clock. It does not know it is useful. It simply obeys the physics written into it at the moment of its formation, and spins, and pulses, and spins again, patient in a way that has no real equivalent anywhere in human experience. We sometimes speak of patience as a virtue, something a conscious being practices with effort, but this is something else entirely, a patience without awareness, without waiting, without the passage of time meaning anything at all to the thing that embodies it. The pulsar is not waiting for us. It was simply there, and we arrived, and we began to listen. And what we hear, when we listen carefully, is more than just a rhythm. Every pulse that reaches a radio telescope has made a long journey. It left the pulsar's magnetic pole as a narrow beam of radio waves, moving outward at the speed of light through the interstellar medium, that thin, cold, ionized gas that fills the space between stars. Along the way, it encountered free electrons, which slowed the lower frequency components of the pulse slightly more than the higher frequency ones, spreading the signal in a way that tells astronomers exactly how much ionized gas it passed through. It may have traveled for hundreds or thousands of light years, and in that travel time, in the precise number of seconds and nanoseconds it took to arrive, is encoded the geometry of everything it passed through, the density of the interstellar medium along that particular line of sight, the gravitational fields of any massive objects nearby, the slow stretching or compressing of space itself, if a gravitational wave happened to pass through the galaxy while the pulse was in transit. That last part is worth sitting with for a moment. A gravitational wave, a ripple in the fabric of space-time, produced perhaps by two supermassive black holes spiraling together somewhere across the universe, would very slightly change the distance between Earth and the pulsar, not by much, by an amount almost incomprehensibly small. But a millisecond pulsar's timing is precise enough that even that tiny change leaves a trace in the arrival time of its pulses. And this is where the pulsar timing array becomes something almost difficult to describe. A single pulsar is a clock, a network of pulsars spread across the sky, each one monitored continuously, their timing residuals compared and correlated. That is something else. That is an instrument, the largest instrument, in terms of physical scale, that humanity has ever constructed or conceived. Its components are not connected by wires or cables. They are not housed in a single facility or even on a single continent. They are neutron stars, scattered across thousands of light years of the Milky Way, each one spinning in its own quiet corner of the galaxy, each one sending its signal toward us without knowing we are here. The baselines of this instrument, the distances between its components, are measured not in kilometers, but in light years, thousands of light years. The entire solar system, with all its planets and moons and the vast distances between them, would be a single point within this instrument. Earth itself, with all its radio telescopes and all its accumulated human knowledge, is simply the receiver at one end. And yet it works. In 2023, multiple teams of astronomers, working independently on different continents with different telescopes and different pulsars, all arrived at the same conclusion. There is a gravitational wave background humming through the galaxy, a low, slow, almost geological rumble of spacetime, with wavelengths measured in light years and frequencies so low that a single oscillation takes years to complete, almost certainly produced by the slow in-spiral of supermassive black hole pairs, objects billions of times more massive than the Sun, orbiting each other across the cores of distant galaxies, drawing closer over millions of years, radiating their energy as waves in the fabric of space. We detected those waves, not with a single instrument, but with the galaxy itself as our detector, using dead stars as our sensors, stars that were never built for this purpose, that have no knowledge of the role they play, that will continue spinning long after the last radio telescope on Earth has gone silent. There is something in that worth noticing. The universe did not build pulsars for us. There is no intention in a neutron star, no design aimed at human convenience. A pulsar is the remnant of a catastrophe, a star that ran out of fuel and collapsed in a fraction of a second, leaving behind this dense, spinning, radiating object as a kind of scar in the fabric of the galaxy. And yet, here we are, lying beneath the same sky that those radio waves fall through every night. Here we are, having built the instruments to catch them, having developed the mathematics to interpret them, having spent decades in patient observation that mirrors, in its own small way, the patience of the pulsars themselves. We did not plan this. We stumbled toward it, discovery by discovery, from that first strange repeating signal in 1967, cataloged with the quiet humor of scientists who briefly wondered if someone else was out there, to a global network of telescopes listening to dozens of pulsars simultaneously, mapping the gravitational murmur of the universe. The pulsar ticked before we were here. It will tick after we are gone. But for this brief window, these few decades out of billions of years, we are here, and we are listening, and the signal is arriving, and the timing is precise. And somewhere in the careful comparison of nanoseconds across thousands of light years, we are learning something true about the shape of the universe. That is enough. More than enough. Let the signal travel. Let the star spin. Let the numbers accumulate in the archives of radio observatories on a small planet orbiting an ordinary star. Somewhere out there, a millisecond pulsar is completing its 716th rotation of this second, and its next, and the one after that. Steady, patient, unchanged. And you, here in the quiet, you are part of the same universe that made it. Rest now. There is a kind of clock that no human hand assembled. It was not designed in a laboratory. It was not calibrated against any standard. It simply spins, a dead star, dense beyond imagining, turning in the dark at hundreds of rotations every second, and keeping time more faithfully than almost anything we have ever built. This is the millisecond pulsar. And to understand why it ticks so steadily, it helps to know what it once was, and what it had to survive to become what it is now. A millisecond pulsar begins as something ancient, an ordinary pulsar, already old, already slowing, spinning down over millions of years as it bleeds energy into space. It would eventually grow quiet, its beam fading, its rotation winding towards stillness. But sometimes, a companion is nearby, a star close enough that when it begins to age and swell, its outer layers spill across the space between them and fall. That infalling matter does not simply land, it carries angular momentum with it, and as it spirals down onto the neutron star's surface, it transfers that momentum gradually over hundreds of millions of years, spinning the old star back up faster and faster until it is rotating not once per second, but dozens of times, then 100, then several hundred. This process is called accretion, and during it, the system glows. The infalling gas heats to extreme temperatures, and the pair shines brightly in X-rays, visible across great distances. Then, eventually, the companion exhausts its outer layers. The flow of matter, slows, and stops. The X-ray glow fades, and what remains is a neutron star spinning at extraordinary speed, often with a quiet white dwarf companion drifting nearby, the remnant of the star that gave it this second life. This is why millisecond pulsars are sometimes called recycled pulsars. They're not young, they are old stars, remade, and something remarkable happens to a pulsar that has been through this process. Its magnetic field, already weaker than that of a young pulsar, weakens further during accretion. And a weaker magnetic field means less braking, less resistance to the spin, so the recycled pulsar holds its speed with extraordinary tenacity. The fastest known millisecond pulsar completes 716 rotations every second. At its equator, the surface moves at roughly 24% of the speed of light, and yet it does not fly apart. The gravity holding it together is 200 billion times stronger than what holds us to the ground beneath us now. That spin is not merely fast, it is stable. This is the quality that makes millisecond pulsars so quietly extraordinary. The best atomic clocks on Earth keep time by counting the oscillations of cesium atoms, achieving accuracy to within about 1 second in 300 million years. That is a precision almost impossible to hold in the mind. And yet, some millisecond pulsars match it. Some exceed it. Certain millisecond pulsars, observed over decades, drift by only a few hundred nanoseconds from their predicted timing. A nanosecond is 1/1000th of a second. The pulsar is that steady. This stability comes from something simple and immense at once. A neutron star contains roughly the mass of the Sun compressed into a sphere about 20 kilometers across. That mass, spinning, carries an enormous amount of rotational inertia. Once it is moving, almost nothing in the universe has the leverage to disturb it. Small perturbations, the faint tug of a distant object, the subtle drag of the interstellar medium, are simply swallowed by the momentum of something that massive, turning that fast. The star does not know it is a clock. It simply spins, as it has spun, as it will spin. Astronomers measure its timekeeping by recording the precise moment each pulse arrives at a radio telescope. Pulse after pulse, year after year, the arrival times accumulate, and in those times, if the model is good enough, almost nothing is left unexplained. The residuals, the tiny differences between predicted and observed arrival times, shrink toward zero. But sometimes they do not. Sometimes the residuals carry a signal, a slight, systematic pattern in the timing of many pulsars at once. Not one, but dozens, spread across the sky, can mean that something is moving through the galaxy itself. Something that stretches and compresses the fabric of space as it passes, altering the distance between Earth and each pulsar by a tiny, measurable amount. Gravitational waves. Not the sharp, brief ripples from two stellar mass black holes colliding, those last fractions of a second, and are detected by instruments like LIGO, which measure the shaking of mirrors kilometers apart. These are something different. These are waves so long that a single oscillation takes years. Their wavelengths are measured in light years. They are the slow, deep breathing of the universe at its largest scales. They are thought to be produced by pairs of supermassive black holes, each one millions or billions of times the mass of the Sun, slowly spiraling toward each other at the centers of distant galaxies. The in-spiral takes millions of years. The gravitational waves it produces are correspondingly vast and slow. To detect them, a single telescope is not enough. What is needed is a network of millisecond pulsars spread across the sky, each one a node in an instrument of almost incomprehensible scale, a pulsar timing array. The principle is this: if a gravitational wave passes through the galaxy, it will alter the arrival times of pulses from pulsars in a correlated way. Pulsars in certain directions will arrive slightly early, others slightly late. The pattern across the whole array carries the signature of the wave. In 2023, several independent collaborations, teams in North America, Europe, Australia, India, China, each monitoring their own set of millisecond pulsars, each combining their data with the others through the International Pulsar Timing Array, announced that they had found strong evidence for exactly this: a gravitational wave background, a low hum of space-time distortion permeating the galaxy. It had been there all along, in the timing residuals, waiting to be read. The instrument that found it has no single location. Its components are scattered across thousands of light years of space. Its baselines are not measured in kilometers, but in the distances between stars. It is, in a sense, the largest scientific instrument ever assembled, and it is made not of steel and glass, but of dead stars, spinning in the dark, sending their pulses faithfully across the void. Each pulse that arrives at a radio telescope has traveled for years, sometimes decades, sometimes longer, through clouds of ionized gas that slow it slightly, through the curved geometry of space near massive objects, through the faint gravitational wash of waves produced by black holes merging in galaxies we will never visit. All of that is encoded, quietly, in the timing. A pulsar's pulse profile, the characteristic shape of its average pulse, is as individual as a fingerprint and far more durable. It persists, essentially unchanged, for millions of years. Some millisecond pulsars have been observed continuously for more than 30 years now, their timing models growing more precise with each passing year, each new pulse adding one more data point to a record that will outlast the careers of everyone who began it. There is something in that continuity worth resting with. A star died. Its core collapsed in less than a second. It was spun back to life by a companion that has since grown quiet. It has been turning, alone, in the dark, for longer than our sun has existed. It did not know we would one day listen. It did not wait for us. And yet the signal arrives, pulse by pulse, nanosecond by nanosecond, carrying within each tiny interval the geometry of everything between there and here. The universe did not build pulsars for us to use as clocks. And yet, here we are, listening. Let that be the last thought for now. Not a question, not a wonder to chase. Just a quiet fact, settling like dust in still air. The star spins. The signal travels. And somewhere in the careful accumulation of arrival times, something true is being learned about the shape of everything. Rest now. There is a kind of stillness that only comes after a long journey. Not the stillness of emptiness, but the stillness of arrival. The pulsar has been spinning this whole time, long before tonight, long before the first astronomer pointed an antenna at the sky and heard something that should not have been there. A rhythm, clean and steady, arriving from a direction no one had thought to look. It was 1967 when Jocelyn Bell Burnell first noticed it, a repeating signal in the data, so regular it seemed almost deliberate. The scientists who gathered around that signal did not immediately reach for natural explanations. How could they? The pulse came every 1.3 seconds, without variation, without drift. Nothing in nature was known to keep time like that. For a brief while, the signal carried a quiet, serious question. Could something out there be sending this on purpose? The designation they gave it, informally, was LGM-1, Little Green Men. It was not entirely a joke. It was the honest acknowledgement that they did not yet know what they were hearing. That kind of honesty is worth remembering. Science, at its best, sits with uncertainty rather than rushing past it. Within months, 3 more signals like it were found, scattered across different parts of the sky. And the question shifted. Not whether something was sending, but what kind of object could spin so precisely, so relentlessly, without winding down? The answer, when it came, was stranger than the question. A dead star. The collapsed remnant of something that had once burned for millions of years. Now compressed into a sphere roughly 20 kilometers across, rotating dozens of times every second, sweeping a beam of radio waves through space the way a lighthouse sweeps a beam across dark water. We happen to be in the path of that beam. That is all. That is everything. Ordinary pulsars spin between roughly once and 30 times per second when they are young. But youth, for a neutron star is a relative thing. Over time, they slow. They radiate energy. The spin down is gradual but measurable, and from its rate, astronomers can read a pulsar's age the way a geologist reads strata in stone. But some pulsars do not slow down the way they should. Some spin hundreds of times per second. Some spin more than 700 times per second. These are the millisecond pulsars, and their existence requires a different kind of story. A millisecond pulsar is, in a sense, a second life. The neutron star was old and slowing and might have faded into silence. But it was not alone. A companion star, orbiting nearby, began to age and expand. And as it did, matter spilled across the space between them, falling onto the neutron star's surface. Each particle of infalling matter carried a small amount of angular momentum, and over hundreds of millions of years, that momentum accumulated. The neutron star spun faster and faster and faster still. This process is slow beyond imagining. Hundreds of millions of years of patient accumulation. The companion star eventually exhausted itself, collapsing into a white dwarf, growing quiet. And the neutron star it had spent so long accelerating was left spinning alone, now turning hundreds of times every second, its magnetic field worn down by age to something far gentler than a young pulsar's. That gentler field is part of what allows the speed to persist. A weaker magnetic field means less energy lost to radiation. The spin down slows to almost nothing. The millisecond pulsar becomes, in effect, a clock that almost never loses time. The best atomic clocks on Earth keep time by counting the oscillations of cesium atoms. They are accurate to about 1 second in 300 million years. That is a precision almost beyond ordinary comprehension. And yet, some millisecond pulsars match that stability. Some exceed it, stable to within a few hundred nanoseconds across decades of continuous observation. Not because anyone designed them for this purpose, but because a neutron star, once set spinning, carries so much rotational inertia that almost nothing in the universe can disturb it. It simply turns and turns and turns. Astronomers record the arrival time of each pulse at a radio telescope. Each pulse is a data point. Each data point is a small, precise measurement of where the pulsar is in its rotation at that exact moment. Over years, over decades, these measurements accumulate into a timing model of extraordinary refinement. And within that model, hidden in the tiny deviations from perfect regularity, there is information. A slight drift in arrival times might mean the pulsar has a companion, something orbiting it, tugging it gently forward and back. This is how the first planets ever confirmed beyond our solar system were found. In 1992, not around a sun-like star, but around a millisecond pulsar. 2 worlds, perhaps 3, orbiting a dead star in a bath of radiation that would strip any atmosphere in an instant. They are not places anything could live, but their existence told us that planets could form or survive in conditions no one had anticipated. The timing deviations can also carry something else entirely. If a gravitational wave passes through the galaxy, a slow, deep ripple in the fabric of space itself, it will very slightly alter the distance between Earth and each pulsar. The pulses will arrive a little early or a little late. The change is tiny, but it is there, encoded in the residuals, waiting to be read. A single pulsar cannot tell you much, but dozens of millisecond pulsars, spread across the sky, observed simultaneously for years. That is something else. That is an instrument whose baselines are measured not in kilometers, but in thousands of light years. The largest scientific instrument, in a sense, that has ever been assembled. Not built, exactly, but recognized. The pulsars were already there. We simply learned to listen to them together. In 2023, several independent collaborations announced what they had been quietly building toward for years. Strong evidence of a gravitational wave background, a low hum of space-time distortion permeating the entire galaxy, thought to be produced by pairs of supermassive black holes, each one containing millions or billions of solar masses, slowly spiraling toward each other in the cores of distant galaxies. Their in-spiral takes not seconds, but millions of years. The waves they produce are not sharp events, but a continuous, almost geological trembling. And the pulsars heard it. Or rather, we heard it through them. 70 millisecond pulsars, monitored by a collaboration called NANOGrav. Similar arrays in Europe, Australia, India, China, their data pooled into the International Pulsar Timing Array, all of them listening to the same slow music. Each pulsar a different ear pressed to the same vast silence. There is something worth resting with in that image. Dozens of dead stars scattered across the galaxy, each one spinning in the dark for billions of years, each one ticking with a patience that has no human analog, and together, without knowing it, forming the most sensitive detector of cosmic motion that physics has yet conceived. The star spins. The wave passes. The pulse arrives a few nanoseconds late, and somewhere, in a quiet room, a number is written down. That is all. That is the whole of it. A dead star, turning. A signal, traveling. A number, recorded. And in the accumulation of those numbers, across years, across decades, across the careers of people who will never see the final result, something true about the deep structure of the universe slowly becoming known. You do not need to hold any of this. Let it settle. The pulsars are still turning. They will be turning long after tonight. Long after all of this. Just turning in the dark, quietly.